Hello and welcome. In this video, I want to take a look at how we calculate the surface area of a parametric surface. So here's the situation. We will be dealing with, we start with the UV plane, and we have a parametric vector function, right? So we have r of u and v equals some x of u and v, y of u and v, z of u and v. So each of these are functions of u and v. And so that's taking this UV plane and embedding it into XYZ space. Okay. So it'll go in as some surface in that space. And in particular, what we want to look at this time is you've got some region, let's say region D here, and that region in particular is being mapped to some piece of that surface. Okay, and the question we're trying to ask is, what's the area? Okay, this is not unlike what we did with the Jacobian back a few weeks ago, right? Where we had UV going into just XY, so we're just changing coordinate system, and we had to decide how a region in the UV space got transformed in the XY space. Now that was all flat, flat in the UV, flat in the XY. Now this is going to be curved potentially. It could be flat depending on the parameterization, but most likely this is going to be curved in some way. And we're trying to figure out what that area is. We call it surface area. Okay, so the way we're going to do this is not unlike many other calculus problems. We're going to cut it up into a bunch of little small pieces and look at what happens in each little piece and then add up all of them, right? So we're going to subdivide the region into little rectangles. So the width of each rectangle down here is going to be some delta u, and the width of it in this direction will be some delta v. Okay. And look at any one of those little rectangles. We're going to take a bigger picture here. We're going to say, one of these UV rectangles is being transformed into some patch of surface in XYZ space. And I'm going to approximate the area of this surface by saying, let's find a tangent line that would be an appropriate length there, and a tangent line that would be an appropriate length there, and then essentially make a parallelogram out of it. And we'll approximate the area of the curved surface by the area of that parallelogram. The thing is, I know how to find areas of parallelograms, because if I've got a vector that points, if I got the two edge vectors here, then I can take the cross product to get what I would call a normal vector. And it's perpendicular to both of those. But more importantly, the length of that normal vector, the length of the cross product, will equal the area of the parallelogram. And so then I just do that for every one of these little rectangles, right? And add them all up. And this is what really looks like a double integral, because you have two variables that you're going to be integrating over. Okay. Now, what are these tangent vectors? Well, the parameterization is taking any point UV and converting it into XYZ. And so essentially any point along this edge is being converted to some point along this edge. But along this edge, let's see, this is like the u-axis here and the v-axis there. So along this edge we have v, because v is a constant. And so it's just a function of u. And this brings us back to the beginning of Calc 3 even, right, when we did just vector functions, that if it's just a function of u along this edge, then we know that the derivative vector will be the tangent vector. Now, it might be longer than we want, or it might be shorter than we want, but we're going to scale it to the appropriate amount, right? So the vector here is going to be parallel to, what did we call the function? This was r? Yeah. So this is, I'm going to call it r sub u, that is the partial of the parameterization of the vector function with respect to u. So each of the components, x, y, and z, will have to take the partial with respect to u. Now, that's the wrong length, because the partial, this vector is going to be essentially the length of this vector is just long enough for essentially one unit of u, right? When you change from whatever value u is here to u plus 1 there, you're going to get an xyz coordinate to start with and an xyz coordinate to end with. And I don't want to go 1 unit in time, or time. I don't want to go 1 unit in u. I only want to go this far. That far is just delta u. So the thing is, if you go that far in one step in u, if I only want to do delta u, how do I scale it down? Well, I just multiply by whatever delta u is. Right? That this is delta u. If delta u is 2, then I want twice this vector. If delta u is a half, then I only want half that vector. If delta u is 0.1, then I only want 1/10 of that vector, right? That this is precisely how far the function changes in 1 unit of change of variable, and I want just delta u change of variable. So there we go. Likewise, over here, on this edge, I have u equals a constant, and so this is just a function of v. So this curve over here is just like, a vector function of one variable and the derivative vector. So that would be r, I'm going to do sub v, meaning the partial with respect to v, partial each component, x, y, and z, taken with respect to v. That vector is the vector that's long enough to do 1 unit of change of v, but I don't want that much. I only want delta v, so I'm going to scale it down by delta v. And so the normal vector that I'm looking at here, this normal vector n, is going to be ru crossed, it's ru delta u crossed with rv delta v. Now, scalars times cross products can be factored out, essentially. Not factored out, but it's a commutative property, really. So this you can think of as take r sub u crossed with r sub v and multiply the result by delta u delta v. And what I want is I want the area of that. So the area is going to be the length of that cross product. So the length of ru crossed with rv, and then times delta u delta v, because again, when you're multiplying a vector times a scalar, the length of that is just the vector times the scalar, provided those are positive, and we will take them to be positive. So that's the area of this little parallelogram. And what I want is the area of all of the region, that is, add up all of those little parallelograms. So take the double integral over the region D of this thing as they get smaller and smaller and smaller. So the surface area is the double integral over D of the length of the cross product of Ru crossed with Rv dA, which is du dv or dv du. We should do an example. So the region that I want to do here, the surface that I want to do for an example is this, it's a cone. So this was one of our examples from the previous video. So in the UV plane here, I've got U between 0 and 1. I've got V between 0 and 2 pi. So this is the region D here that I'm going to be integrating over. But that's being transformed into the XYZ space with this mapping here into a cone here. So notice that the z values are equal to u, and u is between 0 and 1. So this is going from 0 up to 1. U is also playing the role of the radius of a circle. So when U is 0, the radius of the circle is 0, and when U is a half, the radius of the circle is a half, and when U is 1, the radius is 1. So the radius of this circle is the same as the Z value when we get up there. So let's look at these vectors here, because I need to do the partial of R with respect to U. So the partial of R with respect to U is cosine V, comma sine V, comma 1. And the partial of R with respect to V is, what is this? This is U minus U sine V, and U cosine V, and 0. So when I calculate what's called the normal vector, and I take the cross product of those things, RU crossed with RV is equal to I, J, K, cos V, sine V1 minus U sine V, U cos V 0. The first component, actually let's drop down here and say the first component is, what do we have? 0. So I got minus U cosine V. And then the second component, I'm going to do this one backwards. This is minus U sine V minus 0. And then lastly, I've got U cos squared V plus U sine squared V, how do I say that? U cosine squared V plus U sine squared V, which is just U. I'm going to need to know the length of that. RU, this is RU crossed with RV. The square root of this first one squared, U squared cos squared V, plus U squared sine squared V, plus U squared. There we go. Which the U squareds come out in front here, so I've got U. I'm not going to worry about an absolute value because U is between 0 and 1, so it's always positive. I might have to worry if this was potentially negative. But inside, I've got a cos squared V plus sine squared V, which is 1 plus 1, which is the square root of 2. So the surface area now of my cone is going to be the double integral of U times the square root of 2 times dA, and let's see, let's do du dv. U was from 0 to 1, v was from 0 to 2 pi, and I think I can do that. The square root of 2 is just going to come along for the ride on the outside, and then this is a rectangular region, so and it's yeah, so I can just do the integral from 0 to 2 pi of dv and times the integral from 0 to 1 of u du. So this is 2 pi, sorry, this is square root of 2. This integral is 2 pi. This integral is u squared over 2 evaluated between 0 and 1, which is 1/2. So I've got the square root of 2 times pi. The 2 and the 1/2 are going to cancel out, and that's the surface area of that cone. Right? That cone of radius 1 and of height 1 has area square root of 2 times pi. This is generally not a particularly easy integral to do. I mean, it's a fair amount of work to get here, right? You had to take the two partial derivatives, this one, You had to cross those two vectors to get whatever the cross product was. You then had to find the length of the cross product, and we really lucked out that a lot of stuff disappeared there. I mean, it wasn't luck. I picked a simple one for the first example. And then you have to integrate that, whatever it is. You have to do the double integral over the region in the UV plane. And that will tell you the surface area of the parametric surface described by the parametric representation that we had to begin with. Okay. One that I want to challenge you with, I'm not going to do it right here, but I think it's a really good one to try. And that is a donut, a torus. Okay. So think of the torus here centered at the origin. So you got the z-axis going up and the x-axis, sorry, that'd be the y-axis and the x-axis. And so you can think of the torus as being generated by a circle here, and then it's rotated around the z-axis. Now, we could have done this in Calc 2, perhaps, but I want to do this, set this up for you to try parametrically. Okay. So I want to say the radius from the origin to the center of this circle, let's call that A. Right? So here to here is just A. And then the radius of that circle is B. So the parametric representation that we're going to have for this is our, again, this was an example we did in the last video as well, but so the distance from the origin out to this point that you'd get by dropping straight down is A plus B cosine V. And then to get the x-coordinate, I'm going to multiply by cosine U. Same thing, A plus B cosine V multiplied by the sine of V. To get the y component, no, yes. And then do just B times the sine of, so that was a U, this is a U, and this is a V right there. Okay, so this would be the parametric representation of this this donut, right? You rotate that around, the inside goes there, the outside goes clear out there. Calculate the integral. Oh, and this has to go, U and V are both going from 0 to 2 pi. Because U is essentially going to be measuring the angle from the x-axis, and V is going to be measuring the angle up from the xy plane. So to get all the way around, you got to do both of them, 2 pi. So 0 to 2 pi, 0 to 2 pi. The length of RU crossed with RV, du dv or dv du, either way, to calculate the surface area. See what you get. It's a pretty interesting result. Enjoy.